Well, here's what I initially want to talk about today. Kurtmer op amps and OTA circuits. But since Mr. Kimmler rained on the parade, I may delay discussion of the Kurtmer op amps for a little bit. But that's not the reason. But anyway, a review from last time. We looked at the Kurtmer op amp. It was introduced by Wheatley and Whitlinger in '69. Real simple structure. The idea was, this is not the way they presented it, but in the context of the way we were doing synthesis, we said if we could increase the GM of the quarter circuit or the counterpart circuit, we could also increase the gain of the device. And we looked in the small signal parameter domain and saw that we were indeed able to achieve that. But I want to spend some time talking about something else. Homework problem 1, assignment 2, had 2 parts to it. Using the same model of the op amp, obtain the relationship between V out and V in for the circuit on the right. The same model that we use in almost all the standard electronics texts. And then comment on the relative performance of these 2 circuits, and if possible, on why the circuit on the right is seldom discussed. Most people in the class got the first part right. The circuits are the same. But almost nobody rigorously assessed the difference between those 2 circuits. So I've got a question. Are engineers expected to know how to interconnect the basic circuit elements to make circuits?
Yes.
Yeah. Any connection we want to put together with these, we should be able to interconnect. And we may be guided by things that we've seen done in the past, but usually when you're doing design, you have to interconnect things in a different way than they were interconnected before. So we're expected to be able to interconnect these in different ways to make useful circuits, to meet a given set of applications, right? So it's kind of disturbing. So a lot of circuits are never discussed in textbooks. The one that I mentioned is not discussed was this one here. But you can take any circuit you saw in your 230 text, or any circuit you saw in the 201 text, and change the terminals of the operational amplifier around, and those circuits weren't discussed either. So half of the interconnections with op amps are never discussed. Are we leaving out a little, or are we leaving out a lot? A lot. We're leaving out half of them. So you're often guided by what's been done previously, but you need to look at different interconnections usually to solve new problems. And these are the components we discussed in 201 and 230, and half the circuits that involve op amps were never discussed, probably in any of these courses. And of course, we could add to that list some other devices, and those are the devices that are a focus in 330 and in this course and a few other courses, the lower level active devices on the bottom. So most people observe that if you use the ideal models of the op amp, both circuits have a gain 1 plus R2 over R1 times Vn, or an output 1 plus R2 over R1 times Vn. I'm going to look at these 2 circuits in 2 different ways. First of all, I'm going to stay strictly in the DC domain. Practical op amp differs from an actual op amp in that it saturates. So an actual op amp will have a transfer characteristics something like this. Independent of how I put it in a circuit, these are the transfer characteristics of the op amp. And here's a mathematical model. If I assume it's linear, V out equal VDD, as long as VA is bigger than some voltage Vx. It's equal to A, the gain of the amplifier, times VA if the input is between plus and minus Vx. And it's equal to minus VDD if the differential input is less than Vx. That's the mathematical model for the circuit. So now let me consider the negative feedback configuration. For convenience in this discussion, I'm going to assume R1 equals R2 equals R. Not necessary, just made my notation just a little bit easier today. So if I look at this circuit, I can observe that VZ is equal to V out over 2. There's no current that flows in here in our model. So VZ equals V out over 2. And I can take Kirchhoff's voltage law around this loop here, and I can see Vn is equal to Va plus Vz. And of course, the op-amp's modeled by this expression here, irrespective of what I connected in. I can take this first equation, and I can eliminate Vz between those two equations, and I find that the relationship between VA and Vn and Vout is given by this expression here. So this is one expression that relates VA, Vn, and Vout. And here's another expression that relates VA and Vout. So I should be able to eliminate VA between these two expressions and obtain the relation between Vout and Vn. That's our goal, right? That's what we mean by solving the circuit. So Vout equals VT if VA is bigger than Vx. Well, VA is equal to Vn minus Vout over 2. Right here. At the boundary, Vout is equal to VDD. So I can put in then Vn minus VDD over 2 has to be bigger than Vx. And in that case, Vout is equal to VDD. Likewise, I can put in when VA is at the lower limit, then Vout is going to be minus VDD. So I can put in minus VDD here, and I'll see that VA is equal to Vn plus VDD over 2. Right here. And that quantity has to be less than minus Vx. And for Vn between the value determined by this equation and this equation, the analysis we did before applies. Vout equals A Vn, and that relationship was 2A over 2 plus A Vn. That's what you get if you just solve the circuit in this region here where the gain is A, and if A is large, it's approximately 2 Vn. And this is a non-Bernoulli with a gain of 2. So these are the conditions for Vn for this to be valid. I have a solution. I have an output condition now. Instead of conditioning on VA, I condition on Vn. So let's plot this. If I plot that function, for this is the same as saying Vn is bigger than Vx plus VDD over 2, Vout equals VDD. For Vn less than minus Vx minus VDD over 2, Vout equals minus VDD. And in between, Vout is approximately equal to 2 Vn. And this is what we have seen in laboratories and so forth. This is the region where we assume it's ideal op amp and it saturates at plus and minus VDD. Okay, everything good so far? Now let's consider the positive feedback configuration. Again, I'll assume R1 and R2 are the same. These equations change. Vz is still Vout over 2. But now Kirchhoff's voltage law here is Vn is equal to minus Va plus Vz. So this equation changed. the sign of VA flipped. I can eliminate VZ between these two equations and find that VA is equal to minus VN plus V out over 2. That's true all the time, right? Irrespective of what the output is. So now what I do is I want to solve this equation and this equation simultaneously. This equation has VN, V out, and VA. This has V out and VA, so I want to eliminate VA to get the relation between V out and VN. Okay. At this boundary, V out is equal to VDD when VA equals minus VN plus V out over 2. So in place of VA, I can put minus VN plus VDD over 2. Minus VN plus VDD over 2 in place of VA. That has to be bigger than Vx. Of course, Vx is a characteristic of the amplifier. And I can do the same thing on this equation down here. And put it in place of VA. I put in minus VN minus VDD over 2. Minus VN minus VDD over 2, and it has to be less than minus Vx. And in between, if this inequality changes, we leave this region, we go into the middle region. So if I just flip this inequality around, this becomes the boundary where we leave this region. And if I flip this inequality around, I leave region 3, and I satisfy this equation. Now, if I look at what this equation is, I can rewrite this as a range on Vn. So I can say Vn here, put it on the right-hand side. Vn is greater than VDD over 2 minus Vx. And this equation says Vn is less than VDD over 2 plus Vx. So I can write that as one inequality. And say Vn then is between this limit and this limit. Okay. So I'm going to plot this equation. This is now the solution. Is everybody with me? Solve two equations, two unknowns. It just happens that they're piecewise equations. We still solve them. And we get this solution. What have I used? I've used only things that we have coming out of 201. I haven't pulled out terminology. Oh, there's some positive feedback floating around there, or some other terminology that some people include in the answer. Things that are not associated with any theorems you had. They're just words that you pulled out. Make sense? So is there a different performance in two circuits? Yeah, the transfer character is a lot different. Now, what does this tell us? What?
It's unstable.
Maybe. How do you know it's unstable?
Because you have three solutions for the J line.
Yeah.
At any point and
Okay, it has triple valued output.
yes.
We have said nothing about stability yet. We just see this has three different solutions.
But one of them is at equilibrium.
So when you analyze a circuit, assuming the op-amp is ideal, this is the solution you got. But for certain values of Vn, the output could be here, or it could be here, or it could be here. Okay, so this is a circuit that has multiple equilibrium points. It just happens, now we need some more tools to go from here. It just happens that points on that line in the middle here, if you hook the circuit up and start at this point, it will migrate away and jump up to this one or down to this one. Those don't happen to be stationary equilibrium points. The upper and lower ones are, but the other ones not. Do we use, and this circuit has positive feedback. Feedback's to the positive terminal. If we understand what feedback is, This circuit certainly has positive feedback. And maybe we could say the positive feedback is what contributed to these three levels that occur here. Do we use positive feedback circuits very much?
Yeah. Yes, we do.
We do for oscillators.
We do for oscillators.
We do for comparators if we have to use them out there.
Yeah. You know, a lot more positive feedback circuits are used in the electronics community than negative feedback circuits, by far. Every digital latch is basically two inverters in a loop. That's a positive feedback circuit. So we use lots and lots and lots of positive feedback circuits. So I'm going to consider this now from a different viewpoint. I'm going to consider an amplifier that has a single pole. And we're going to design our op amps so that they have a single pole characteristic. So the gain can be written as the pole times A0 divided by S plus P0, where P is the pole and A0 is the DC gain. And this is assuming that the amplifier is operating in the non-saturated mode. Since the circuit is soon to be linear, the output voltage is equal to the differential gain times V plus minus V minus, which is Vn minus this voltage here. And this voltage here is R1 over R1 plus R2. I call that beta, Vn minus beta V out. I can plug A of S in that equation from the first equation to the second one and solve for V out in terms of Vn. And if I do, I get this for the gain expression. And I guess you can observe that this amplifier in the open loop it started out with a pole at P. This was the open loop case. A pole at minus P, excuse me. And in the closed loop, that pole got multiplied by 1 plus A beta. If beta was 1, like it was in the, or 1/2 like it was in the previous example, and A naught was 100,000, this pole is much, much higher frequency. So there's one pole here. That's the open loop pole. And here's the pole with feedback. And this is closed loop. Long ways away. Now let's go to the positive feedback structure. Amplifier gain doesn't change. Still modeled by the same characteristic. But now, V out is equal to A of S times V plus minus V minus times beta V out minus V in. So this changed. I can solve those two equations simultaneously, and I find the closed loop gain is equal to minus P A naught divided by S minus P beta A naught, approximately, if I neglect the 1 plus. And this closed loop pole now is in right half plane. So in this case, we start with the same open loop pole, but now the closed loop pole is way over here. Okay. So since the pole's in the right half plane, this amplifier is unstable. Does this mean the amplifier is not useful? Does it mean it's not useful? One thing about circuit designers, somebody throws something away and somebody will grab it and say, I can find a use for it. when I was a student, if you burned out a bipolar transistor, you would see if the base emitter junction was still good. If it was, you had a diode. Okay? That's when transistors cost a little bit. Does it mean it's not useful as an amplifier? How many think it's not useful as an amplifier? How many think it is useful as an amplifier? Can you show me how it's useful as an amplifier?
No, but there has to be one.
Yeah. Yes.
Is it a competitor?
What?
Is it competitor?
Well, I'm saying as an amplifier, not as a comparator. As a linear amplifier.
Oh, as a linear amplifier.
No. Anybody want to change their vote? As a linear amplifier, think it's useful. Tim, do you have an idea?
No, I was changing my vote.
You're changing your vote. Okay. So this happens to be a filter structure. It's one of the most popular active filter structures that exists. Bell System used to use this in a lot of telephone systems. Millions and millions and millions of copies of this were used. It's one of the best bandpass filters that's known to exist. So you have what's called a bridge T network. If you put the resistor down here, here's a T with a bridge across it. So this is a bridge T feedback network with a finite gain amplifier amplifying the voltage from here to here. K is typically a small positive gain. And we'd like high input impedance, ideally infinite impedance on K, on the structure. Okay? Very popular filter structure, one of the best that exists. Widely used. We don't use a lot of these active filters today. We will use switch capacitor circuit or something else, but it had a long run. So, how do you build an amplifier, finite gain amplifier? Well, let's go in and put the amplifier that we've been looking at in. And that circuit looks like this. Is that how you approach it? That's a divide and conquer approach, right? If you do it, and you go in the laboratory, you'll find that the filter is unstable. So we've got a problem. We built the circuit, you put a finite gain amplifier and analyze it, looks great. Put a good, stable amplifier with a gain K in, and your filter doesn't work. Bummers. What about sticking this circuit in? Double problem now, because this circuit is unstable, right? This circuit's unstable because it has a pole in the right half plane. Stick this circuit in here. Oh, but it has the right. If the op amp was ideal, it still has the right gain. It still has a gain K0. So here's that circuit. And this is the circuit that Bell Labs used. So, does that change our perspective on things? Is this circuit useful as an amplifier?
Not by itself.
Yes.
On its own, I would say no.
Maybe not on its own, but what we needed here was an amplifier. So we stick this amplifier in, it acts like an amplifier, and it makes a great filter. Is this a situation where two wrongs make a right? So we need to be careful on drawing conclusions about whether that positive feedback amplifier is a useful amplifier. Because many times we don't use an amplifier by itself. Many times that amplifier is embedded in a system someplace. So, let me ask the question. If you use that amplifier in this filter, is that amplifier still unstable?
Aren't you introducing two extra poles in that closed loop?
Well, filter has poles. That's right. So you have two poles that you want from those two capacitors in that bridge T feedback network, and one that you don't want due to the op amp.
Yes.
So is this amplifier still unstable in this filter?
And itself is unstable, and the system is always stable.
Well, you, think so, because look, you have two feedbacks. You have one to the negative and one to the positive.
Yeah, I guess.
Did we have a zero somewhere that canceled out our original right half plane?
Yeah.
No? No. So I think you guys are on to what's going on here. It's the stability of the system we're concerned about. When I ask the question, is this amplifier stable in this configuration in the circuit here? That's not a fair question to ask. Stability is not addressed by a subpart of a circuit. Stability is only addressed by the system as a whole. So I shouldn't have even asked the question, is this amplifier stable in this circuit? Stability applies to the whole structure. It doesn't apply to a subpart of a circuit. Make sense? And this circuit has poles in the left half plane where we want them. It performs very well. So I have some more comments to make about stability, but I wanted to hit this one right now since we did the homework 2 assignment on it. Before we do compensation, we're probably going to have to come back and look at some of these issues again. Is feedback a simple concept?
I mean,
You can get fooled on it sometimes, can't you?
yeah.
And it's important to keep an open mind and ask questions why certain things are done. Let's go back to that current mirror op amp. When it was introduced as an alternative to an op amp, but it also found quite a few applications open loop. So the OTA is often used open loop instead of in a feedback configuration. The OTA has excellent high frequency performance. If you look at op amp, the op amp's frequency performance is usually horrible. Their pole is typically in the 10 radians per second range. They're starting to die before they ever enter the lower end of the audio range, the op amps. An OTA's gain, since you use an open loop, will oftentimes still be having a nearly constant gain up to several hundred megahertz. So it's got excellent high frequency performance. If you look at the GM of that current mirror op amp, the GM was determined by GM1 of the differential pair. GM1 was proportional to the bias current. So as we change the bias current, we change GM. So we could say GM is programmable by a DC bias current. Okay. For BJT circuits, if you use BJT instead of MOSFETs, GM is proportional to IEBC. For MOS circuits, after it's fabricated, GM is proportional to the square root of the bias current. If you build an OTA with MOS circuits and you change IEBC over 4 orders of magnitude, you get 2 decades of adjustment of GM. For a BJT, if you change IEBC, you can show that you can get 5 to 6 decades of adjustment of GM for a BJT by just changing the bias current. So we have programmable GMs. So let's look at the circuit right here. There's an open loop application. I'll put a resistor on. And if it's a transconductance amplifier, the output current is equal to GMVN. And the output voltage is the current times the resistor, so the output voltage is equal to GMRVN. Agree with me? Okay. So now GM is controlled by ABC. If R is fixed, the voltage gain can be adjusted
By changing GM.
by what?
Changing GM.
By changing GM, by just changing the DC bias current. Now, it's pretty easy to build a circuit that converts a DC voltage to a DC current. So now you can have a microcontroller that has a DAC on it that might have a voltage output. You convert that voltage to a current and let that current adjust the IABC. And now you've got a linear circuit, an amplifier circuit here that's digitally controlled. Analog circuit that's digitally controlled with a DC voltage. That's pretty nice, isn't it? What if you had a current mirror? And IABC was one output on a current mirror. We had 10 amplifiers. All 10 amplifiers have the same IABCs. Then one DC current that goes to the input of the current mirror would adjust simultaneously the gain of 10 amplifiers. Take them all up or all down together. How else can you do that? If you scavenge old test equipment, you'll find one way they did it. They took potentiometers and ganged them on a stack. Instead of having one potentiometer on a shaft, you put 2 or 3 or 4 or so forth. Those got real expensive when you start ganging them together, right? Here you get as many as you want. One DC control voltage or current will control as many as you want. Inverting amplifier we can obtain by just changing the terminals of the op amp OTA around. This now is a voltage controlled inverting amplifier. If you think of the OTA as a circuit element, how many elements does it take to build the non-inverting amplifier? 2, an OTA and a resistor. If you do it with an op amp, how many does it take? 3, op amp and 2 resistors. If you want to build a non-inverting amplifier without having a common mode, a big common mode input problem, you probably need a buffer on it or something as well. How about this circuit? You take an OTA and connect the output back to the input. Let's see what its characteristics are. So we're going to take this OTA. I'm going to connect the output back to the input. And I want to look at the IV characteristic, put a voltage here, let a current flow here. Of course, this is a one port, right? So this one port has an impedance. So I can see that the current here is equal to, this current here is GMV. So the current is equal to minus GM. I'm sorry, this current here is minus GMV because I'm in the minus terminal. So I can say I then is equal to minus a minus GMV or plus GMV. Or V over I is equal to 1 over GM. And V over I for the one port is the input impedance. So the input impedance of this one port is 1 over GM. So this looks like a resistor of value 1 over GM. Well, maybe I'm just trying to do business for the semiconductor industry. I could take one resistor that costs 1/3 of a cent and have a resistor.
That's the area.
But that takes area. We can make these OTAs really small. So now I've made a resistor with a small amount of area out of an OTA. One OTA gives me a resistor.
Don't you have a potentiometer?
What?
Don't you technically have a potentiometer if we can control that?
Yep. So I can adjust the bias current, and now I have a current controlled or a voltage controlled resistor, equivalent potentiometer. This works at low frequencies and it works at high frequencies. If I flip the terminals to the OTA around, what? Negative resistor. Yeah. Who would want a negative resistor? Is that one of those things you ever get when you throw? Would you like one? What?
To see what he can do.
Could it ever do anything useful to you?
It's not.
I'll suggest one thing it might do that's useful. Let's assume you have an inductor. I can't throw all these away because yeah. I'll take you up on it if this one fails too. Thanks.
Right, no one's.
So far, I'm good. Unfortunately, you wind up some wire to make an inductor, and you end up with a resistor here. And if you have a loss in your inductor, the quality of your circuits that use that inductor are bad.
Cancel it. No way.
Okay, what do I have here?
This defies everything.
It's for real. It works great. And they can be used for that purpose.
Yeah, it's
Okay, so we have a negative resistor.
a voltage gain. Yeah, it's an amplifier.
What?
It's a voltage gain. Whatever you lost in RS, you're gaining in minus RS.
Yep, that's exactly.
So you're
So from here to here, it's one port, and it looks like SL.
I don't believe it.
Believe it, it works.
it's a shock.
What if I put that resistor on this output here? Then I have an amplifier that's voltage controlled. How much gain control do I have on this? 2 degrees of freedom, 2 bias currents. If I use bipolar devices, I can control this one over 6 orders of magnitude. I can control this one over 6 orders of magnitude. How much gain control do I have over this? A lot. Enthusiasm. How many orders of magnitude? 12. 12 orders of magnitude. Can you imagine? I can't give you an application right now for an amplifier that you want to operate over 12 orders of magnitude, but they'll do it. Okay? If I flip the terminals on the OTA around on M1 or GM1, I get an inverting amplifier with the same control range. What if I put a capacitor on? If I put a capacitor on, I get V out over Vn is equal to Gm over Sc. That's an alternative to, see, that's a non-inverting integrator. See how I can build that. Probably the way you built this if you did it in 230, you probably started out with an inverting integrator. Oops. Is this an inverting integrator? And then we invert that. Okay, so this V out over Vn, if these are the same, this is equal to 1 over RCS. Okay. How good a frequency response does this circuit have with the op amps? Okay, but not great. Op amps are dying before we even enter the audio frequency range, right?
Yeah.
Everything's downhill once you enter that audio frequency. Once you get past the pole, everything is downhill. How many components does it require? 6 components. 6 components, and it doesn't work very well at high frequencies. This circuit here, how many components does it require? 2, and it operates very well at high frequencies. If I want the inverting integrator, just change the terminals of the OTA around. and I get the inverting integrator.
Are OTAs more realized in BJTs or MOS?
But both can be used. We're not going to go into details in this course, but you can show that the signal swing, if you adjust the GM by very much with the MOS structures, your signal swing gets pretty small. With the bipolar structures, you can show that the signal swing is independent of the bias current. So you can get large range of operation and still good signal swing. Many applications, we don't need to have multiple decades of adjustment. We just want to tune for process variations. So if you build a filter in MOS structures, you might use a MOS structure. You plan on adjusting it plus or minus 20% because you want to take care of process and temperature variations. Make sense? So some comments about OTA-based circuits. We can realize arbitrary complex functions, high order filters, and a lot of other things. Circuits are often simpler than what can be obtained with op-amp counterparts. They inherently offer excellent high frequency performance, can be controlled with DC current or voltage. We talked about current, but we can easily convert a DC voltage to a current. They're often used open loop rather than in a feedback configuration. There's other high output impedance op-amps that can use OTAs as well, but this kind of came out of initially the work of Wheatley and Whitlinger. So if you look at a lot of the filters that are used today in high-speed communication circuits, many of those filters are going to be OTA-C-based filter structures. Some limitations. The linearity is not that great. There's been quite a bit of work on linearization schemes of the OTAs, but a lot of times in high-frequency communication circuits, linearity is not critical. Frequency adjustment and accuracy is, and they can be controlled. Signal swing may not be limited, but it can be pretty good too. And if you use the bipolar structures, or if you don't have to adjust your GM over a very big range with the MOS structures. The circuit properties are process and temperature dependent. The GM is typically temperature dependent. But again, we can build circuits that compensate for temperature changes in these circuits. Well, let's get back to that. Do we have time to talk about Mr. Kimmler's question? So I've got one thing I need to discuss first, and then maybe we can get back to this for about 1 or 2 minutes. I've got to travel on Monday to DC. And then I'm going to miss 3 lectures the following week. What I would like to do is try to see if we can find an evening, maybe sometime next week, where I bank a couple lectures, maybe try to do a marathon. Look, I get punished worse than you guys do because I'm the one. So if we could find a night sometime next week where we might try to pick up 3 lectures, pick up the Monday lecture, and then pick up 2 of the lectures that I'm going to miss the following week. Of course, then you get a break at 10 o'clock the following week. Can we find a night that might work? I won't get back until late Tuesday, but Wednesday night or Thursday night would be good for me. Is Wednesday night a possibility?
Wednesday night is a 6 to 9 lab. Yeah, Thursday night would work better.
Thursday night?
Thursday night.
Thursday night?
After.
Okay.
5:32.
Yeah, after 6 o'clock.
6 o'clock? Okay, so we'll try to do a 6 to 9 lectures Thursday night of next week. Okay? I don't really have time. I was going to answer Mr. Kimmler's question today, but I guess we're going to have to wait until Wednesday to answer Mr. Kimmler's question. Are there any questions? Yes. Is there a reason? An OTA is a type of op-amp. So I guess I can't, pedagogically, I can't tell you. Op-amps are much more popular than OTAs, but there are certainly a lot of applications for the OTAs as well. Okay, anything else? That's all for today, thanks.
So that's Thursday.
That's the end of Election 11.